I'm an MCA. Today we have to see some basics of alternating current. An alternating current in the simple form is, we call it as sinusoidal AC. I've told you this earlier. And this is represented graphically like this. This is one cycle of AC. Now, during one cycle, current increases from 0 to a maximum value I0, then decreases to 0, then changes to minus I0, that is direction changes, and then becomes 0. This is one complete cycle of AC. The time required for this one cycle is called the period of the AC, represented by capital T. A number of cycles repeated in 1 second is called frequency F. F equals 1 by T. And omega, this is called angular frequency of the AC or pulsatance of the AC, given by 2 pi into frequency or 2 pi by period. Now, what is one cycle? How will you define one cycle? One cycle of AC is a set of positive and negative values including 0, which is repeated at a regular time interval. That is one cycle of AC. Number of cycles repeated in 1 second is called frequency. In India, frequency of AC is 50 cycles per second. In certain other countries, frequency is 60 cycles per second and so on. And the time required to complete one cycle is called a period. So in India, AC distributed in India, period is frequency F equals 50 cycles per second, so that period T equals 1 by 50 seconds. Now we have to measure AC. How will you measure AC? Direct current is measured by a moving coil ammeter. Moving coil ammeter is based on magnetic effect of current. That is torque received by a coil carrying current. Torque depends on magnitude and strength of the direction of the current. Since AC changes its direction every second, a number of times every second, it is impossible to read AC alternating current by means of moving coil ammeter, because the coil torque, direction of the torque goes on changing, and because of inertia it won't move and it will give 0 reading. Or a moving coil ammeter always reads the mean value of the current. Mean value over a cycle is always 0 because half of the cycle is plus, the other half is minus, so average is always 0. So an ordinary moving coil ammeter shows 0 reading. Therefore, to measure alternating current, we have to choose an effect of current that is independent of direction of current. There is such an effect called the heating effect of current. Heat developed in a resistor does not depend on direction of current. Whether it moves from one end to the other or from that end to this end, heat developed is always I squared R T, because there arises the factor I square. Whether it be minus or plus I square is always positive. So how do you fix a standard for measuring current that we call as RMS value of alternating current? The procedure is like this. Suppose you want to measure strength of an AC. You pass this AC through a resistance for a known time period and measure the heat generated by the resistor. Then you pass a direct current through the same resistance and for the same time period, and see that the heat developed is the same in both. Then that the direct current is chosen as the RMS value of this AC. So RMS value of an alternating current is equal to the direct current, which generates the same amount of heat in a resistor for a time as generated by the AC. So if I is the direct current which passes through the resistance R, then heat generated during the time t, where t is the period of this AC, is I squared R into t. If an AC to be measured is passed through this resistance, heat developed during the time t, you can compute it as integral I squared R into dt. This is the total heat developed by the AC during the time period t. These heat values must be equal to define RMS value. So equate these two. That R would go, then you get IDC square equals 1 by T. I0 is a constant, you can take it outside. So 1 by T into I0 into integral 0 to T of I is I0 sine omega T. That I0 is taken out. Then sine square omega T dt. And the final answer you will get it as I0 by root 2. So this IDC is chosen as the RMS value of the current. So alternating current is measured using the heating effect of current, because heating effect does not depend upon direction of current. And IDC is identified as the RMS value, IRMS. Usually we will omit the subscript and we write capital letter I to denote RMS. IRMS equals I0 by root 2, or peak value of the current by root 2. In a similar way, you can show that RMS voltage V equals V0 by root 2. Then mean value over a cycle, as I said earlier, is always 0, because one half is plus, the other half is minus, so the sum of the two will be 0, then sum divided by 2, that is the average. That is always 0. So we define mean value of 1/2 of the AC. That is, by calculation, you can show that it is I mean over 1/2 of a cycle of AC as I0 by pi. We will need this value when you study rectifier circuits in electronics. So these are the basics are related with measurements, cycle, and so on. Then we have seen that resistance, capacitive reactance, and inductive reactance. We know that resistance, when you pass alternating current through a resistance, ordinary resistance, we call it as ohmic resistance, a metal wire, that's all. The resistance is independent of frequency of the AC. Resistance is a constant of that metal wire. So if you plot a graph between resistance and frequency or pulsatance omega, that is 2 pi into actual frequency. This is in radian per second and F is in cycles per second. The graph will be a straight line parallel to the frequency axis because it does not depend on frequency. Now, capacitive reactance. Capacitive reactance is the opposition offered by a capacitor against the flow of alternating current through it. The formula is Xc, capacitive reactance, equals 1 by omega C, where omega is 2 pi F, so 2 pi Fc. Cross multiply this to form Xc into omega equals 1 by C. 1 by C is a constant of the capacitor. So this is of the form Xy is a constant, or vertical quantity on the vertical axis into quantity on the horizontal axis is a constant, that is the equation of a rectangular hyperbola. So graph between Xc and omega will be a hyperbola. For direct current frequency, there is no change in magnitude or direction. So frequency of change is 0. Direct current means omega equals 0. So when omega equals 0, Xc becomes 1 by 0 into C, or 1 by 0, that is infinity. So as resistance increases, as frequency of the AC increases, reactance frequency decreases, reactance increases. And finally, for DC, frequency is 0 and reactance becomes infinitely large. What does it mean? A capacitor offers infinite resistance against the flow of direct current, or capacitor will block the passage of DC. It won't conduct DC. But at the same time, as omega increases, Xc decreases. That is, capacitor passes or conducts alternating current, especially alternating current of high frequency. Similarly, when you take an inductance coil, reactance of inductance coil XL equals L into omega, where L is the coefficient of self-induction or self-inductance. This is of the form Y equals mx, equation of a straight line starting from the origin. So graph between inductive reactance and the frequency of the AC is a straight line passing through the origin. Well, for DC, omega equals 0. That means XL equals 0. So, an inductance coil conducts direct current easily, whereas a capacitor blocks direct current. As frequency omega increases, inductive reactance also increases, that is, it will block, but it offers high reactance against high frequency AC. So the behavior of the two entirely different. So we can use a combination of capacitor and inductance coil to separate AC and DC from a mixture. See, if a mixture of AC and DC flows through this channel or this line, you can separate them. You connect a capacitor like this and an inductance coil like this. Inductance coil offers very small reactance on DC, so the DC will flow through this branch. Whereas capacitor will block DC, it will pass AC. So AC will choose this path, DC will choose this path. Thus we have separated AC and DC from the combination. Such a combination is called filter circuit. This is a very essential component in almost all electronic circuits. Thank you.